So I basically, this talk will be mostly historical, and if there's time, I'll do a brief discussion of a recent paper I wrote that is more or less an application of heavy quark effective theory or heavy quark symmetry. And so that's the plan for the talk. I'm not, even though it's mostly historical, I'm not one that pays a lot of attention to the history of the development of subjects. Steve Weinberg passed away recently, sadly, of course, did. Howard Georgi, who also talked from a historical perspective in this series, less so. But these are the areas I decided to talk about are things that occurred on my watch. And so I have some, recollection of them and some sense of what I thought was important or interesting and different about them. Of course, it's colored by my own point of view and also affected by somewhat of a failing memory. So I want to apologize right from the start for the important work that I'm going to leave out. Sometimes because of just you can't pack everything in, and sometimes because I just didn't remember. Well, okay. So what I'm going to do is I'm going to do two subjects. So one is what you might call QCD corrections, short distance corrections for the effective Hamiltonian for weak non-leptonic processes, Kaon decays, hyperon decays, and of course it's also applied in other cases, charm decays, B-meson decays. And then the other topic will be sort of the early development of heavy quark effective theory. And I could have also talked about about the developments in effective field theories for nuclear physics. But I decided not to, partly because in that application, it's really only the part at very low momentum that I feel confident about. In nucleon-nucleon scattering, that's momenta that in a range much greater than 1 over the scattering length, but much less than the scale of the strong interactions. But my collaborators in the work that I did in that area, David Kaplan, Martin Savage, they think, and they might be right, of course, that there's a broader range of applicability. We just need to figure out a few more things. So I thought it might be better. I think it's a really interesting area, and it might be better if one of them spoke about it. Okay, so talk has 3 parts. I'm hoping to get through 2 of them, which is, so the first part is integrating out W bosons and including strong interactions for Kaon decays. Of course, it's also hyperon decays. And I wrote it like this because when I look back at the papers, these are papers, for the most part, I had looked at when I was a graduate student. I was a graduate student from 1977 to 1980. And so I found some new ones that I hadn't realized back then. But let me move over the pictures of faces so I can see more of my slides. Yeah. So, and I'll talk a little bit about some of them. But what struck me when I looked at the collection of them was how physical they were. They were after a particular physical problem they were trying to address with this formalism, and they really focused on that much more than development of the formalism, although there were some on the development of the formalism. So this started in 1974, right after asymptotic freedom. And of course, it was already known by then, probably for a very long time, that that if you have a heavy particle, you can integrate it out, get an effective Hamiltonian that's some non-renormalizable operator. For example, at tree level for the weak interactions, the famous V minus A theory of Feynman and Gelman. And it was even known at the loop level that this occurred. For example, there was a calculation, don't remember the year, by Gaillard and Lee, where they looked at short distance processes. Well, they looked at rare kaon decays and KK bar mixing. And for example, they integrated out the W bosons and the charm quark and got an effective Hamiltonian for KK bar mixing. It was a 4-quark operator. And so they realized, or the community clearly realized before this, that if you have a heavy particle, you can integrate it out and represent its effects by an effective local interaction. And that's true not just at tree level, but even at the loop level. But what was new right after, right at this time was asymptotic freedom. And asymptotic freedom meant that there were short distance effects due to the strong interactions that you could compute and include in your effective Hamiltonian. And in particular, these are the effective Hamiltonians for non-leptonic decays, because we want to have the quarks in the game, and for the semileptonic decays, the operators of partially conserved current. It's not renormalized. So so that was the thing they were after. And in particular for non-leptonic decays, there's this piece of phenomenology called the delta I equals a half rule. And if you take the weak Hamiltonian, you can decompose it under SU3 and under isospin. So under SU3, it's 27 left, octet left, under SU3 left cross SU3 right. And under isospin, similarly, there's a I equals a half part and an I equals 3/2 part. The 3/2 part lives in the 27 and the isospin a half in the octet. And it was known, it's true, that the isospin a half part of the amplitude is just suppressed by a lot. Sorry, the isospin a half is enhanced by a lot. It's roughly a factor of 20 in the amplitude, 400 in the rates. And it's true not just for the kaon decays, but also for the hyperon decays. So this was a great mystery for many years. There were people that thought it was beyond the standard model at that time. Theory really required new physics. And the first papers on these strong interaction short distance corrections to the weak Hamiltonian, they were motivated by whether those corrections could give an enhancement to the I equals a half part of the Hamiltonian. Could they explain this phenomena? And so I listened to Howard Georgi's talks, and what he did was he put up the titles and abstracts of papers and talked a little bit about them. And I decided that I would follow that style. So I tried to cover the screen as little as possible with the titles and abstracts. And so if I didn't have the journal in that, I would write down the reference here. So there were two very early papers calculating the QCD corrections to the weak Hamiltonian, one by Gaillard and Lee, and one by Alterelli and Maiani. And I don't think when I was a graduate student, I had really looked at the one by Alterelli and Maiani. But I think I knew about it. I just assumed it was the same as the one by Gaillard and Lee. And then I decided, well, I better look at it last night just to make sure. And I couldn't. Because, they didn't have when I went out to Spires, they didn't have the preprint and the journal wouldn't let me look at it. So that's some critical remark about journals. And one thing to realize, these papers are very close. I'm sure they were independent. There was no archive back then. You didn't find out what the other person did the next day. They would basically mail out hard copies of their papers to people they thought might be interested. And then they would do a general mailing, sort of the lowest class of mail that went all over the world. It might take months to get those papers, and they would be bulk mailed, several of them at once. As an author, you might mail out individual ones to your friends or famous physicists you thought might be interested. Wasn't a very democratic system. So I think Paul Ginsburg, I mean, he did a great thing for physics, making it much more democratic. So these two papers, here I've written out the operators in the effective Hamiltonian for weak decays, for strange mesons and hadrons that have strangeness. So they're Q1 to Q6. So Q2 occurs without any strong interactions, then mixes in Q1. And these papers, I believe, well, certainly this one, were about renormalization of Q1 and Q2. And you do find that the isospin a half part is enhanced due to short distance physics, but it's nowhere near enough to explain the delta I equals a half rule. And then again, shortly after, there's this paper by Weinstein, Zakharov, and Schiffman, and there's another one after I'll mention, where they realize there's more operators in this effective weak Hamiltonian. There's operators, as they say, with right-handed fields. And in this list of operators on the right-hand side, that's Q3 to Q6. And the way they talked about it, the way they explained it in their paper, if I recall correctly, is they arise from these diagrams like this one here. Of course, it wasn't a bottom quark. I pulled this off the internet. It was a picture with the bottom quark. And then I decided I could have found one with a strange quark or one without labels and just put the S on it. But so the situation here is S to D. But I thought it was nice to put this up just to remind myself and the others attending the talk that, of course, these developments that were done in the context of kaon and hyperon decays, they also apply to non-leptonic decays of heavier mesons, just changing the mixing angles and the labels of the quarks, charm decays, and bottom decays. So they realized that diagrams like this could induce these extra operators. It's kind of funny to draw this diagram and say it. I mean, these are local operators. This doesn't look very local, but at the level of the diagram, what happens is this vertex gives you a q squared, which cancels the 1 over the q squared in the gluon propagator, and gives you a local operator. Let me look at the time. I have a tendency to go 15 minutes already. Okay, well, obviously I got to pick up the pace off this. Okay, why isn't it forwarding the? Oh, there it goes. Okay, and here's another paper on the same subject. So not too much later, there was a paper by Ed Witten on the title here is Short Distance Analysis of Weak Interactions. And this is a very pedagogical paper that sets up the formalism and how you compute things, how you match at the W scale, using dimensional regularization, and you scale down your subtraction point. And when you're using a lower subtraction point, basically you're including, it's not really a cutoff, but you can think about it as including physics up to that subtraction point, and the matrix elements, the operators, and the higher momentum physics has been moved into the coefficients. And when I was a graduate student, when I read this paper, it's when I really, I would say, understood the method the best. But even Ed was kind of embarrassed to write a paper just on an explanation of things that, he sort of knew. I mean, Gaillard and Lee, Schiffman, Weinstein, Zakharov, they probably, or Schiffman, Zakharov, yeah, Schiffman veins, they probably understood all this, right? I would assume they understood all this, and I think he did as well, but he really gave a very cogent and clear explanation of it, and also did some new applications. So the first way I became well known as a graduate student was locally at SLAC by writing a paper with Ed Witten. And after that, when I was introduced, so SLAC, it was like the center of the universe when I was a graduate student there. Almost all the important members of our field would come to visit for a little while, and you know, sometimes shorter visits just to give a talk. And it was really a remarkable place to be. So one of those visitors was Ed Witten, and I asked him a question about these penguin diagrams. And it was a question someone had asked me and I didn't immediately know the answer to, or didn't know the answer to. And that was, you know, it's true you get a q squared that cancels the gluon propagator, but this doesn't look like a very local operator, right? Like a very local effect. So non-local things, they should be in the matrix elements of these operators, and it's only the very short distance physics that goes into the coefficients. So so I asked Ed what was going on, and he knew right away, and I would assume many of the other authors would know right away, and that's that really, if you're calculating the operator mixing, you should calculate these one particle irreducible diagrams. And then what happens is these diagrams, when you sum them all up, they end up giving you a covariant derivative on the gluon field, and then you can use the equations of motion to relate it to q bar gamma mu q summed over TAQ summed over the flavors. So that was what was going on, and we decided that there was probably enough that I might not be the only one that was confused by this fact, and that it was worth writing a little pedagogical paper on the subject. So there I am, co-author with Ed Witten on probably his least cited paper. And it's sort of nice that you got to go to the third letter of the names to determine the order of the authors. And what I remember most about this collaboration was just how nice Ed was. He explained it to me. You know, he said, "Oh, Mark," and then I called him up. There's no internet back then. I called him up to talk about whether we should write a paper. And he said, "Oh, Mark, I think," yeah, well, he didn't say, "Oh, Mark." He said, "That's a good idea. Why don't you write the first draft?" So I wrote a first draft. I mailed it to him, not emailed it to him. And he sent back something, you know, completely, you know, much better written, with a very nice note saying how wonderful my draft was, and he just made a few changes. There were other things done in this area at the time. For example, there's another operator, sort of a magnetic moment type transition between the quarks, and it doesn't get induced in the operator mixing until 2 loops. And in a very nice paper, Hill and Ross calculated that. Let me just see where I'm going for one moment. Okay. And then there was, I haven't put the paper here. There was a short, because it really was not about effective Hamiltonians all. It was mostly a piece of phenomenology. My thesis advisor, Fred Gilman, and I wrote a short paper that said, look, if these penguin type operators are responsible for the delta I equals a half rule, let's say they dominate it completely, then those operators, you know, they involve the top quark. And if you have Kobayashi-Masukawa CP violation, I guess it wasn't known whether that was the origin of CP violation at the time. We're talking like 1979, around then. But if you thought that, then these diagrams would also give CP violation in Kaon decays when you change that to a strange quark. And CP violation in decay amplitudes, that's characterized by the CP violation parameter epsilon prime. And so we thought epsilon prime might be very large if those operators dominated the amplitudes. And then after that, there were a few papers that went and redid the calculation of the effective Hamiltonian, including all 6 quarks with a focus on the CP violation. And again, the emphasis was very physical. It wasn't so much developing any formalism. Well, by now the formalism was well known in any case. It was really very focused on how big would CP violation in the decay amplitudes. Epsilon characterizes the CP violation in KK bar mixing, and it's epsilon prime that characterizes it in decay amplitudes. So Fred Gilman, my thesis advisor, and I wrote this paper saying epsilon prime might be very large. I think we said 1/20. It's more like 10 to the -3. It's been measured long since, well before now, but after our work. And so there were 2 papers almost at the same time that extended the effective Hamiltonian, including all 6 quarks, and focused on the CP violation. And then, excuse me, I'm looking at the time again. Okay, we're doing okay now. I sped up a bit. Yeah. So, and then there were some papers that did a similar thing for the effective Hamiltonian for KK bar mixing, because you want to have just the whole picture, all the QCD corrections, all the short distance physics accounted for, all the parts that you can do analytically done. And so that's what I would call the early developments for the effective Hamiltonians for non-leptonic weak processes, in particular, the inclusion of short distance physics. These were all 1-loop calculations, and much of this has been done beyond that. In particular, my friend Boras really played a large role in improving things to higher orders, which you certainly want to do. But my discussion here is the early history. Okay, so now I'm going to switch topics, and I'm going to talk a little bit about heavy quark. Oh, here's an interesting remark I made when I was first writing up the slides. Oh, let's see what it. Oh, I already corrected it. Yeah. So one thing that's odd, but it reminds me to say something. One thing that's odd is that so Schiffman, Weinstein, Zakharov, they proposed this explanation for the delta I equals a half rule. I'm not sure we even know now what role those diagrams play in the delta I equals a half rule. I don't think we're confident. They should contribute to it. It seems intuitively clear at some level, but I don't think it's obvious how much. And in particular, when they did their calculations, in order to have those operators be coefficients of local operators, you have to scale down below the charm quark. You have to take your subtraction point well below the charm quark to even imagine logs of the charm quark, or logs of the charm quark mass divided by the subtraction point are large. And so they would go down to something like alpha S equals a half the subtraction point, and try to make estimates based on that. So that's clearly not not rigorous, but they were trying to do phenomenology, and they understood all of that. And if you want to really stop your running at some subtraction point mu where you can justify the perturbative analysis of the running, only 1 or 2 loop or normalization, you have to pick a mu such that alpha S is in the perturbative regime, and that's liable to be a subtraction point above the charm quark mass. And then those operators, they're not in your Hamiltonian, they're in the matrix elements of operators. So I'm not sure what's known about that. Lattice QCD in principle can address that, but you'd have to have dynamical charm quarks, I think, to have confidence in that. And I'm just not up to date on the status of what's happened there. Okay, so now I'll go on. So what I want to do now is talk about some early work on heavy quark symmetry and heavy quark effective theory. And basically, I took the literature up to 1990 and included sort of 2/3 of what happened in 1990. And after 1990, it just exploded. There'd be so many papers. I certainly couldn't do a reasonable job of it. And one thing to think about when I discuss this is that when you have a new method, a method that lets you do things, sort of the mark of its importance in my mind is what can you do that you couldn't do before? It's not just or somehow didn't understand the physics well enough to do before. Maybe you could have in principle, but somehow the insights from this way of framing it let you do it more. It's not just that it makes it easier or makes it more convenient. Sometimes it makes it so much easier that you can do things you couldn't do before. So I think that's something to keep in the back of your mind with regard to heavy quark symmetry and heavy quark effective theory. And the other thing is that we have kind of a love affair with non-perturbative physics. It's considered in many ways, I don't know, harder or deeper than perturbative physics. I'm not sure that's really true, but we should keep in mind what heavy quark effective theory or heavy quark symmetry lets you say about non-perturbative physics. So as I said, I listened to Howard's talk, and there's one early paper by Nussanov and Wetzel that's often mentioned, with the early insights on heavy quark effective theory, and I couldn't remember why. And I think Howard said he couldn't remember why. A lot of them you can tell from the title what they're about, but this one I couldn't tell. And so I looked inside the paper. I'm sure I looked inside when I was younger. And the reason is they talk about the beta D transition. And they make some arguments that the corrections to the normalization at zero recoil, where you just say a bottom quark changes to a charm quark, where they're both at rest, let's say in the rest frame of the decaying B meson, should have very small corrections. They use a language that higher Falk components to the wave function don't contribute, radiation of gluons is suppressed. So it's not a very model independent discussion. And, depending on your nature as a physicist, you might, or, you might or might not include this as one of the papers that led to the development of heavy quark symmetry. But this is the reason why this discussion in their paper, that it's sometimes included in the list of one of the earlier papers that led to the those developments. Yeah, okay. Yeah, you can see discussing the history, I'm not awesome at it, but oops, not awesome on my slides either. Okay, but these papers I'm going to discuss next, they clearly played a role. So first, there's these papers by Schiffman and Voloshin. So Schiffman and Voloshin are clearly two of the pioneers in the development of these heavy quark methods, and Voloshin passed away quite recently, actually. It's very sad. And but anyways, they wrote a very early paper on the subject, Sorry about that. Okay, so there was this early paper, and they were talking about the decay constants for heavy mesons, and they realized that there was regions of momentum space where virtual momenta are below the bottom quark mass, but above the charm quark mass, that are still perturbative. You should still be able to use perturbative QCD. And those logarithms should be able to be summed, and that you can indeed do that. And they also realize that that then the decay constants for B and D mesons would be related. So there's some relation. It's not just that you can do the perturbative QCD corrections, but that the matrix elements are also related. And for example, here's two heavy mesons with masses MQ and MQ prime, and this is the anomalous scaling that you get with alpha S, and this is related to the anomalous dimension over the beta function in this regime. The region of momenta from bottom to charm, it's there for the B meson decay constant, but not for the charm. There was also an early paper, Schiffman, Uraltsov, Voloshin, Kaons, where they talked about meson mixing, and in particular, heavy meson mixing, and that you could, because the B meson was heavy, you could relate that to matrix elements of local operators. So this is sort of the beginnings of the heavy quark methods for inclusive processes, if you'd like. And after those two papers, although we didn't know they existed at the time, David Pollitzer and I basically did the same thing as in this paper, where we realized there were these logarithms that we could compute. And part of the reason we realized it is that I got a phone call from Joe Polchinski that basically, those days it was phone calls, who asked me, Mark, aren't there logarithms you can compute in B meson processes from momenta below the bottom quark mass, but above the QCD scale? And we had worked together a lot as postdocs on more speculative things than this, but he knew that my graduate work was on this type of physics, and so that I was someone he could ask about it. And I said, yeah, that makes a lot of sense, but I haven't really thought about it. Let me talk to David. And so why did I want to go right away to talk to David? Because, you know, I understood a lot about QCD physics, but David Pollitzer really understood QCD physics at a remarkably deep level. And so I thought he would have insights right away, which he did. And so we worked it out. And then later, I think David found this paper. So another thing we realized in a subsequent paper is that there really is an effective field theory formalism you can use that's going on here. And that's that the heavy quark is a static quark, and we represented it as a Wilson line, and we redid the calculation of what we call this effective field theory using a Wilson line. And I can't tell you how silly I feel about this paper. It's a good paper, I think, but in many ways I feel funny about it, because you know, we use this Wilson line. Why didn't we just write out the Feynman rules in the static limit? You know, it's not so hard to derive them. Why did we stick with the Wilson line? I don't know. I don't know the answer to that. I'm sure we would have been able to do that. Somehow we just didn't realize. Sometimes I say about things like that creativity is at a premium. It's surprising what sort of simple, sort of semi-obvious things after people don't do. But anyways, that's what we did in this paper. And after those papers, there were a couple of papers by Nathan Isker and I, and Nathan Isker sadly has also passed away quite young in his early 50s, I believe. And he was one of my mentors when I was an undergraduate at University of Toronto. And yeah, anyways, so one time I was going back to Toronto and to visit family, and I'd always go into University of Toronto to visit and talk physics with Nathan at the time when that happened. And so I did it this time as well. And then what we realized was that, look at all these things, relations between matrix elements for decay constants, they're really symmetries. And symmetries at the level of any other symmetry. You can understand, there's generators, you can understand what you get in terms of commutators, of, you can derive it the way you would the consequences of any symmetry. So first we did it in the static limit. We wrote one paper. And then the next year when I visited, or maybe this one was over the phone, and the second one was a visit, I don't remember, we realized much more. We realized that this symmetry could be applied at non-zero velocities, and that related different quarks with different masses traveling at the same velocity, not the same momenta, so it was a little bit unusual. And we realized as well, yeah, I'm using that phrase a lot, oh well, that if you look at B to D and B to D star semileptonic decays, that all the form factors in those decays, there's several form factors, were related to a single form factor. And those form factors, they parameterize non-perturbative physics. They might have a short distance part from these large momenta, but these processes, the form factors, there's a low momentum part of that, non-perturbative physics. And so the symmetry aspect gives you a lot of power over non-perturbative physics. We also realized that in the static limit, when both the bottom and, well, this paper realized that. So all the form factors are one function, and at zero recoil, that function is normalized. It's a charge of the symmetry, if you'd like. And it's hard to know, if you look back at the earlier papers, whether whether they would have said it was a symmetry or realized that the fact that the B and D meson form factors are related, basically it was it was at some level understood, if not said, at least at zero recoil. But saying it like a symmetry, and certainly its use and power when you go away from zero recoil, was not appreciated. So since this is my work, it's probably the best work I've done in my whole career, almost certainly. So I gave here the relationship between, let me look at the time again. 7:40, okay. So I gave the relationship here that you get in the heavy quark limit, heavy bottom and charm quarks. And then I took this paragraph from our paper that describes what's going on. It really says it's a symmetry. It mentions the unusual aspect that it relates states at equal velocity, or fields at equal velocity, but different mass and therefore different momenta. And after this paper, I think there were many physicists who realized there was just a lot to do. Not just perturbative physics, not just these new types of logarithms, but also non-perturbative aspects of the strong interactions. And I'll come back to this later, but it has a lot of similarities with the other analytic tool for non-perturbative physics, which is chiral perturbation theory for the physics of kaons and hyperons. There's sort of many overlaps in the things that can be predicted, but I think the array of applications of heavy quark symmetry or heavy quark effective theory really is larger, basically because the B meson has a large mass, so that there's perturbative aspects that it impacts as well as the non-perturbative ones. There's many more states available to you to look at as well. There's not just the ground state multiplet. The D and D star mesons are degenerate in the heavy mass limit, but there's excited D mesons that fall into multiplets. And then there's also relations for heavy quark symmetry for B meson transitions to them, and those can also be studied experimentally. So there's a much richer array of applications in this case, even though if you looked at courses taught in particle physics, I think most courses would teach chiral perturbation theory as an important tool, but I'm not sure the fraction of courses that would teach heavy quark symmetry and heavy quark effective theory as an important tool. Not quite sure why. Okay. So now I want to go to papers that occurred after our paper. We're already into 1990, our second paper with Nathan. And then there was just a lot of developments. So there's one paper by Bjorkane, of course. Bjorkane is an amazing physicist. One of my proudest moments of a graduate student, as a graduate student. So as a graduate student, I had done this work on CP violation, and CP violation is really tricky because there's all this phase freedom in the Lagrangian. So a lot of phases don't really represent physical effects. They're just artifacts of how you write the Lagrangian. And so very senior physicists like Bjorkane, BJ, people called him or call him, would come to me, well, he came once, but and basically ask me a question about CP violation and how it worked. I mean, physics, particle physics is really a democracy. I mean, you go ask whoever you think knows something that'll be useful to you. And in this case, it was me. So I got to know a lot of senior physicists in our field because they visited SLAC, and I had this sort of piece of expertise, excuse me, that they would talk to me about. They had be interested in talking to me about. So after my paper, with Nathan on heavy quark symmetry at non-zero recoil, BJ wrote a paper on the same subject where he introduced an important way to do the group theory, which was Nathan and I did it using commutators, the old-fashioned way. But there's other ways to do group theory. For example, you can write down tensors with indices to do the rotation group, and there's this method with traces that everyone uses now that appeared in this paper. And he also did a lot of more physical applications, some rules for decays to excited states. He put it all in a talk that he gave. It was written up, a SLAC preprint, but it appeared in this talk. He never published it, even though I encouraged him to publish it. I think he said to me, Mark, it's fine. I don't need another paper. But he had things to say. He wanted people to see it, so he made the SLAC preprint and gave the talk in this venue. So I mentioned before that Nathan and I didn't write out the Lagrangian, even the static limit. And then there was this paper that occurred by Eichten and Hill, where they wrote out the Lagrangian. They really did much more than that. It's an excellent paper. Of course, everything I'm mentioning here are excellent papers, but still, this one really impressed me at the time. And they included 1 over m corrections to the Lagrangian. They did the matching. They renormalized the operators. If at least that's my recollection of this paper. But again, they worked in the static limit. And then there was everything happened very quickly. You can see it's 1990. And the order that I'm presenting them here is not necessarily the order they came out in the journals. They were so close together, people didn't know what the other people were doing. So I guess this one is actually before this one, but there was a paper by Howard on the effective theory for, and what fascinated Howard, and I think what is really one of the most interesting aspects of this whole thing, is the fact that when you have these heavy quarks, the heavy quarks at a given velocity, non-perturbative QCD doesn't change that velocity. It's only, and so it's almost like a super selection rule. The heavy quarks have a particular velocity. Each velocity sector is a separate sector of the theory. And he wrote out the Lagrangian in this way of looking at it, and stressed that these symmetries, they exist at every velocity. It's a spin flavor symmetry because you can exchange bottom and charm quarks. And so he, in my mind, he really put his finger on the most interesting, or one of the most interesting aspects of the physics, and elaborated that. In particular, this effective Lagrangian is much easier to use to compute, at least when you add also the QCD part, making this a covariant derivative. Sorry, looking at the time again. Oh, I got to speed up a bit. Okay. Ben, also in 1990, he was at Harvard then. So you can get these effective theories just by taking the limit of the Feynman rules of QCD. You can get the vertex gamma mu goes to V mu, and the propagator goes to I over V dot K. But of course, you usually just take that limit at tree level. There's all these higher order corrections that are going on. And so, and in particular, the mass shifts order by order in perturbation theory of a heavy quark. And so he wrote a paper that illustrated that this was the right effective theory to all orders in perturbation theory, how to take the mass shift and things like that into account. There was a paper by Howard's graduate student, Adam Falk, Howard, Ben, and I, where where the renormalization of this universal function was calculated. Its shape actually changes. It also used this trace formalism to make the predictions. I mentioned to you there's only one form factor in beta D and D star decays. There's actually a very simple way to understand that David Pollitzer pointed out, just by using heavy quark symmetry on helicity amplitudes. And he wrote that up in a little paper that I am showing here. So these papers that I've mentioned so far, they're mostly doing things at leading order in 1 over the heavy quark masses. Then there were papers that included the 1 over mass effects in the semileptonic decays, and something called Luke's theorem was realized that there's no 1 over m corrections in the semileptonic decays, both baryon and B-meson decays at leading order in 1 over m. And that goes by the name of Luke's theorem. This might be the last of the papers in 1990 I'm going to mention. And this was a paper on inclusive semileptonic decays. And it really set it up in a way that, and did the calculation, if I remember right, at leading order, but it set it all up to do higher orders in 1 over m, and think about things like 1 over m corrections to those inclusive decays, which was developed in more detail a couple of years after this paper. But this paper really set it all up. Okay, so I've taken you to most of what went on in, well, maybe it's 2/3. Uh-oh, why can't I turn on my phone to see what time it is? 7:53. Okay. So there was a lot that followed. I haven't mentioned exclusive decays of bottom baryons, semileptonic decays, perturbative and non-perturbative corrections to exclusive decays, weak decays, these corrections I just mentioned to the electron spectrum and semileptonic B decay, combining heavy quark symmetry with chiral symmetry, inclusive weak radiative B decay. In many respects, it's similar to chiral symmetry. In chiral symmetry, one of the applications of it is to get VUS, this element of the CKM matrix, to high accuracy. These methods, you can try to get VBC to high accuracy, and also VUB with inclusive methods. Well, even exclusively, heavy quark symmetry tells you a few things about the exclusive decays. But there's also others. Yeah, but there's all. So the next thing I want to mention is the similarities with chiral SU3 left cross SU3 right. Well, I was just talking about that. So again, it's getting CKM matrix elements. If you think about SU3 left, SU3 left cross right, the strange quark mass, it's going to work sometimes pretty well, but the strange quark mass is kind of heavy. Sometimes it might not work so well. And the charm quark mass is kind of like the strange quark mass. You might expect sometimes there'll be substantial corrections to heavy quark symmetry because the mass is not extremely heavy compared to the scale of the strong interactions. There's even an analog of this theorem, Luke's theorem, in chiral SU3 left cross SU3 right. It's called the Adamello-Gatto theorem, that for example, matrix elements of the weak current, K to pi, there's no linear corrections in the strange quark mass to those matrix elements. It lets you get VUS better than you might naively expect from those methods. If you ask how well it works, I'm taking a paper from Lattice QCD to illustrate that. Surprisingly, I never could find any analysis by the experimental groups where they tell me how well it works. Probably there's something by now. But anyways, at one point, Zoltan pointed out this paper where they look at B to D. There's probably papers on B to D star now. And remember, there was, well, I showed you just one form factor. That's like H plus here. H minus is 0 in the heavy quark limit. And you can see that the lattice, this one goes to 1, so that these are the lattice results, and as a function of W, and it goes to 1 at 0 recoil, and you can see this one's much smaller. And someone might, eventually it could be, or maybe we're already there now, that the lattice is so accurate and you have such complete confidence in it that the way you get the form factors will be that in order to get the value of VCB from exclusive decays will be from lattice QCD. In my mind, that does not diminish the value of heavy quark symmetry. For example, when you see plots like this, don't you want to understand why H minus is much less than H plus. We don't want to just put things on a computer. We want to understand it. Now we can understand it from a very, and also understand why this is so close to 1. We can understand that now based on symmetry reasoning. That's all I wanted to say. I'm really not doing justice to very many people. There were other people also in the 1990s who did important work on heavy quark symmetry. It just became hard for me. For example, there were papers where there were 2 charm quarks in the final state, several papers along that that I've left out here. And certainly afterwards, there were many people who took a leading role in the field, did many original and novel things with heavy quark symmetry and heavy quark effective theory. Now the methods are understood. There still might be some wrinkles in the future. You never know, but it sits there still as a tool to use when appropriate. Just like chiral perturbation theories is still there as a tool, and you bring it out now and then under cases when new applications come up, mostly driven by new capabilities on the experimental front. Thank you.